Now let me try to set up the file. I think I everything. There. This up. Still not good enough. Let me see. Let me enlarge it even more. It's gonna be a little bit tougher to see everything now. Let me see. Is that gonna work well? Well, it might be easier if I make it a little bit smaller. Would this size be fine if I want to see? Yeah. Or from the back? Are you okay? Fine. It's all right. Okay, great. Thanks for letting me know. So I think this size would work. Okay. So the talk today. Are we starting? Absolutely. Okay. All right. Thanks. So the talk today is going to be really straightforward. I mean, mathematically. Coding-wise, I mean, it requires a little bit. We're going to see how it goes. So with Link, but the mathematical part is pretty straightforward. We start from an old friend. You've seen that previously in precalculus. So suppose that we have a function. It's a quadratic function. We're going to say that is a quadratic function opening up. So the constant a is greater than 0. I would like to ask how to solve an optimization problem that minimizes this quadratic function over all the real numbers. Actually, what you should have. Okay, good. Audio is disconnected. Good. All right. So this is what we would like to do. We've seen that in precalculus already. The way to do that is straightforward. If as soon as you learn derivatives, take derivatives, set that to 0, and it's a linear equation. I'm asking that we can do that using calculus, because it's a precalculus. So how to solve it? Here comes the terminology, of course, beforehand. This is mostly some terminology in optimization. I'm just going to mention it over here because throughout the talk I might mention them sometimes. A x for this minimization problem is called a decision variable. The function of this minimization problem is called the objective function. We're going to say that we're solving an optimization problem. The goal is to solve the optimal solution. Optimal solution usually I'm going to write it down as x star. Definition of optimal solution for a minimum problem is a solution x star such that function value is the smallest among all of them. So basically, for any other solutions, the objective value should be larger or equal to what happens at x star. So without calculus, how are we going to be able to do it? Well, I mean, if we use precalculus knowledge, the only thing we can probably use relating to a quadratic function is quadratic formula. So there is a straightforward way to do it. I mean, we take a look at the quadratic formula. We know what the quadratic formula is: negative b plus or minus square root of determinant over 2a. Then take a look at that graph. We know that the parabola is like symmetric. So if I take the average of the two roots, that's going to give me the bottom of this parabola, and that's it. I know many of you are going to say that I'm making a mistake over here because I did not consider the case when there's no root. But I'm only giving you the idea. I'm not really solving this problem in my solution paper. Okay, so I'm basically trying to figure out what kind of thoughts I would like to do when I'm doing that in precalculus class. So this is the idea. So after this idea is developed, I take a look at the average of those two. I look at the middle of the two roots. It's straightforward. And I realize that that point x is negative b over 2a. So as soon as I realize this, I can continue my idea and actually try to solve this in precalculus class. The reason is because whenever you know that you have two roots, that means your function you should be able to factor it based on the roots. And now because I have a in front of x squared, your function should look like a times x minus the first root times x times the second root. Pretty straightforward. Now I'm going to multiply everything. After I multiply everything, I realize the sum of the two roots should be double the amount of my minimum. And I plug in my minimum over here. I realize I see something like x squared minus 2 times constant times x. So that should give me a complete square. And then I'm going to write it down as a complete square. There are constants I need to worry about, but I'm only cleaning up my thoughts. So it makes sense. And then it looks like the function I'm looking at this stage should probably look like the following format. A times x minus x star squared plus a constant. I don't know what that constant is. I don't want to compute it. Suppose I'm in an exam. I don't really want to compute it. I want to figure out an easy way for me to write down what that constant is. Well, there is a cheating way of doing it. I'm gonna take a look at left-hand side, right-hand side. Plug in x star. If I plug in x star, this term is gone. So the constant is gonna be f of x star, right? As I said, I'm doing this in an exam. I don't know how to solve it. I'm trying to figure it out in the exam, and I'm done. Okay, I'm ready to write down my solution. Now, my solution is going to be the following. Okay, so based on my observation, I'm going to start writing it down. Okay, so it is trivial to observe that f of x is equal to a times x minus x star plus f times x star, and therefore squared. Sorry. And because this a is greater than 0, because square is always greater or equal to 0, so I have a greater or equal to f of x star for all x in R. So we're done. End of story, end of proof. I'm done. Submitting my paper to the teacher. Okay, kind of makes sense. I mean, from my side. As my student, I do that a lot when I was a student. I mean, the student side, of course, not so much. I mean, when the professor is grading something like this, obviously there is something that you are skipping. Okay, so there is definitely something that I'm gonna be missing in my previous solution. So how am I gonna be? Well, how am I going to be verifying, that my proof is actually right? Let's actually do that in the same way in a software. Okay, so this time I'm gonna pull up a software. I'm gonna do that in Link. So the way I'm gonna do is the following. Okay, so here the claim is that I'm having any three real numbers A, B, and C. I'm claiming that A is greater than 0. I'm gonna define my quadratic function in this way, and then I'm gonna claim the x star to be exactly the value I computed previously, and my statement of the result is that for any x, the function value at x is greater or equal to the function value at x star. Okay, so that's it. How am I going to be able to prove it? The proof I'm given is the following. I'm going to introduce the function f, introduce the x star, and introduce the x. So currently, this is the status of whatever we have on play. Okay, this is whatever we have, and the conditions are the following. We have A, B, and C that are real numbers. We have an assumption that A is greater than 0. Let me move this around. Okay, so we also have a function that is defined in this way. It's a quadratic function. I have an x star that's defined in this way. Here is my goal. Okay, so all I'm trying to do is trying to use some mathematical logic to prove, based on my condition, that given any x, f of x is greater or equal to the f in x star. So this is really what I'm trying to prove. This is like the statement of the question in the exam. I'm going to try to do that in the exam format. So first, I claim as I wrote down in my previous solution, I'm going to claim that my function is going to be defined in this way. So this is my claim. I'm saying that I'm assuming that this claim is true. Okay, so I'm going to prove that claim later. But the claim is that there exists a constant. I don't know what that is. I'm just saying that my function, the quadratic function, can always be written in this way, like a times a y minus x star. I plug in x star already, of course, plus certain constant. So this is my claim. And I proceed with my proof, assuming my claim is true. And then I'm going to go back and prove the claim later. So that idea seems to be all right. Okay, so how am I going to really, going forward with the claim? So with the claim that's given, what I'm going to do next is that based on my claim, there exists a constant. So I'm just going to assume that constant is null. So there is a certain constant that's already over here. Okay, there is a constant. And then there is a statement that my function is equal to this format plus a constant. Now, what I'm going to do is that I'm going to plug in the definition of the function. So previously, the goal I'm trying to prove is fx is greater or equal to f of x star. Now I'm going to start plugging in the value of the function at x, the value of function at x star. Okay, so this is the value of function at x. This is the value of the function at x star. Now, over here, I'm going to simplify this statement because I know what x star is. So I'm going to plug in x star inside. I'm going to plug in x star. Okay, so this is what I'm trying to prove. Okay, if my claim is true, then all I need to prove is this one. Now, please be aware of all I'm doing is basically, at this stage is basically, plugging things. I don't do anything extra, right? Now I take a look at the last line. Let me actually move over here, so that most of you actually see the bottom of the screen. Okay, so the bottom line is what I'm trying to prove. So take a look at this last line over here. This is what I'm trying to prove. In the last line, I realized that there is something I can remove immediately. There is this negative plus the same positive number, so I should be able to cancel them. And therefore, I claim that this is true. This is trivial, so I'm really gonna say in my software that you can use a certain way to verify that easily. Okay, so this part is done. That means the left-hand side is gonna be equal to 0 now. Okay, so let me get it from here. Okay, so at this stage, I am gonna apply the result I've just said. I said negative number plus this positive number is equal to 0. I'm gonna start plugging in. All I need to is to show that this is greater or equal to 0, which is kind of straightforward. I have an assumption that a is greater than 0. I know that the square of any real number is non-negative, and therefore multiplying those two together, I should have greater or equal to 0. So I'm done. Okay, so this is the proof, assuming that my claim is true. Does that make sense? I mean, if you follow, what I have on the computer, it actually, makes perfect sense. And then after I'm done with this part, I need to start, proving my claim. And the way I'm going to prove my claim is actually the same way I wrote down in my solution. Although it looks weird in my solution that we're missing something, but I can actually do this. The reason is because what I'm going to do is that I'm going to try to prove this, and then I'm going to say that, I need to show that this is true for any y. So I'm just going to say that I'm going to introduce any y. I'm going to plug in the value of a function f. I'm going to plug in the value of x star. This is what I'm trying to prove. Okay, it's a mess. I wrote in my solution over there that it's trivial to verify. Over here in my software, I'm going to tell it to use a certain tactics, certain operations to verify it for me, and it's done. It actually verified everything for me and claimed that there is nothing left to prove. So I'm done with this result. The difference between this proof and the proof wrote down is probably that if I submit this to my professor, I'm not gonna say, receive that there is work to be done. Okay. The reason is because the difficult part of the work is actually being handled by the software Ling as tactics. So with the help, I don't actually need to do anything. I just needed to simplify everything for me. And after everything is simplified, I'm done, and that's the end. So with Ling, all you need to do if you would like to try to prove certain statements is first write down the statement, and then start proving it. And this is what we call the goal that we would like to achieve when we are actually trying to prove. So you have conditions, or the formal name is hypothesis. So we have hypothesis. Based on the hypothesis, you would like to prove a statement. This is also called the goal. And if you are able to reach the goal at the end, you're done. The benefits of using this software package is that when it tells you that there is no goal to do anymore, it constitutes actually a formal proof, and it's formally verified. So Ling is what we call a proof verification software, or it is also known as a interactive theorem prover. So all you need to do if you need to prove something in Ling is perform all the operations. So so this is the old friend that we had. How about we move forward with calculus 1 knowledge? So if we do calculus, then it's straightforward. Here, please be aware that I'm actually modifying the problem a little bit because of something related to the necessary and sufficient condition of optimal solutions. But I mean, for now, we're just going to assume that optimal solution exists. The question is to solve the problem. Solution we have is straightforward in calculus. You compute the derivative, set derivative equal to 0, compute the critical point. For this problem, optimal solution exists. And we learned in calculus that a local extrema of a function is going to be a critical point. And therefore, because there is only one critical point, this critical point is automatically a local extrema, and in this case, global optimal solution. So we're done. And we know this thanks to Fermat's theorem. This is a page I got from Stewart's calculus book. And this is Fermat. This is a mathematician that is a couple hundred years ago. And Fermat's theorem is a famous theorem that we would like to prove in our class, in my talk today. And well, to write it down in this space, we can just for simple consider only the local minimum case. When we are talking about local extrema, it could be max or min. We are only gonna consider the min case, but well, obviously I run out of margins, so I don't really see any margin that's large enough for me to finish the proof. And obviously this is a quote that's done by the right person, but the wrong context for sure. So the actual proof is actually in Stewart's book. I'm not going to cover this proof. I'm going to cover the concept of proof later really quickly, and try to do that in Ling. Fermat's theorem, I mean, as far as I know, there are three, the ones you've seen a lot. The first is this one in calculus, and then Fermat's little theorem, you do that in number theory, and then there is Fermat's last theorem, which I wish I could understand, which has been proven by Andrew Wiles 350 years after it has been proposed by Fermat. Fermat's last theorem is actually quite related to Ling nowadays. We're going to talk about that later. So back to Fermat's theorem in calculus. The proof idea is kind of straightforward. Okay, The way to prove the calculus theorem that we've seen is actually by taking a look at the slope. The idea is that, for example, this is the local mean. So we take a look at the slope. Taking a look at the right, the slope is going to be greater or equal to 0. Taking a look at the left, the slope would be less or equal to 0. And therefore, I mean, if the derivative exists based on our observation, the derivative should be both greater or equal to 0 and less or equal to 0, and therefore it has to be 0. So that's how this proof is done. We are able to actually prove this in Ling. Let's actually take a look today. Regarding Ling's verification, I'm doing the trivial work today, obviously, by showing the Fermat's theorem in calculus. Fermat's last theorem, there is actually an ongoing project of proving the Fermat's last theorem in Ling. So if you take a look, there is a Fermat's last theorem project in Ling, and that was led by Kevin Buzzard. And I think they've made lots of progress right now. There is still active discussion on the Zulip channel about their progress. I hope I can follow, but I'm the person doing optimization. I know nothing about number theory, unfortunately. So I hope I can understand a little bit of it in the future. But let's go back to the one that I could handle, the simple one, a simple case in Ling. This is something that's actually straightforward. So the calculus 1 results. How are we going to be able to prove it in Ling? The statement of this theorem is actually really straightforward. That's it. Take a look at the bottom of this screen. All we need to show is the following. Given this is the statement. We have a function, univariate, single variable, and we have a point A. We have the derivative at A, which is we call f prime. So f prime it should actually be f prime of A, obviously. That's the correct mathematical notation instead of f prime. But I mean, in this program language and in the look of it, it's just going to be stated as f prime. Okay. So the idea is that we have a condition that A is a local mean of f. We know the derivative at A is f prime, and the goal we're trying to prove is that f prime is equal to 0. First thing to do, I'm going to do is I never mentioned how Ling defines local minimum, right? So we need to do a little bit in Ling to change this notation to the notation we are familiar with. So what's the definition of local minimum that we are familiar with? The notation we are familiar with usually is something that looks like this, using a sigma epsilon delta kind of language. The idea is that we're going to say that A is a local minimum if there is a very small neighborhood such that within this neighborhood, the function value is always greater or equal to the function value at A. So formally, the idea is that there exists a width of the neighborhood, which we call delta, is obviously positive, such that for any length delta x that's within this length delta, the function value at any point within this interval is going to be greater or equal to the function value at A. I'm going to skip the part about moving from the original definition to this definition, but I've already finished the proof over here. Okay, so that's regarding the statements. We also need one more statement. For this statement, as soon as I have this statement, I can write it down in a more detailed way. I'm going to say that there exists a delta. So I know exactly what that delta is. So say I know this delta. And I know that the property of the delta is that it's greater than 0. And for any delta x in this interval, the function value is greater or equal to f of A. So with the more detailed description, I can remove the original description of local minimum I wrote before. So this is the status of the proof. Now we're going to try to think about how it's done formally in Ling. So how are we going to be able to prove it? So the idea of proving that is the following. First, within this interval, so I have a function over here, and by definition, it's a local mean. So there is this very small interval from a minus delta to a plus delta. Well, actually, let me move it a little bit wider. So say this is the interval instead. First, I'm going to show that for any x in the right part of the interval, the slope is going to be greater or equal to 0. So the notation over here in Ling is that IOO states a interval that is open to the left and open to the right. So IO now makes sense. And therefore, the statement is that for any x in this interval, I want to show that the slope is greater or equal to 0. That's it. That's all we need to show. And continue from here. All I need to do is that I introduce any x. I know that x satisfies this assumption. And then what do I mean by slope? I need to, I need to plug in the definition of the slope function. Now, slope function is basically the difference of function value on the numerator over the difference of the variables in the denominator. And you can do much simplifications because this is this slope function is a fraction, and x is greater than a, so the denominator you can do some cancellation and stuff. I'm going to skip that. I'm going to ask Ling to do the simplification for me. And Ling does this simplification. After the simplification, the statement that the slope is greater or equal to 0 becomes the following. All I need to do is to show that for any x that is between a and a plus delta, the function value f of x is greater or equal to the function value at a. I have a assumption originally, and all I need to do is plug in the value of the specific x and compute the specific value of delta x. Think about it. Suppose I have any point x, then the distance from x to my a in this case is x minus a. So that's going to be my delta of x. So I'm going to plug in to get this modification of the previous assumption. What I'm going to do next is that if we take a look at this one, and try to think what we need to do in this proof. There is a plus x minus a. Obviously, we can cancel that. There is x minus a, and we know that x is greater than a, so this x value is obviously x minus a. So that's something that we're going to have to do in our computation if we are asked to show our work in our solution sheets. But I'm just simply going to ask Ling to do the simplification for me and be aware of this condition, a is less than x, and be aware of the condition that absolute value of positive number is itself, and simplify everything for me. And after it simplifies everything for me, I realize that I have this statement over here. This statement says that as long as this condition is true, the inequality is going to hold. So I'm going to apply this hypothesis, and then all I need to show is to show that this is true, which I already know from here that a is less than x. So which is here. X is less than a minus delta. And because x is less than a minus delta, x minus a has to be less than delta. I could tell Ling to do this job for me, or I can tell Ling to try to figure it out for me using certain rules. So Ling is going to figure this out for me. And by doing it in this way, Ling is going to be able to show that, whatever that is to the right, the slope is greater or equal to 0. And by the same strategy, this is the part of the Ling that you cannot skip. If we are doing that ourselves, we can say without loss of generality. But for Ling, you're going to have to finish everything again. So you're going to have to show again that the slope at the left is less or equal to 0. It's similar, so it's almost copy and paste. And then I have the conditions. I don't really need this original condition about local mean anymore because I've transferred it into the condition of the slope. All right, so now I'm ready to finish the result. Here is the part that becomes a little bit tricky. I never told you how Ling defines that the derivative exists. Okay, we know from calculus the definition of the limit, the definition that limits, that derivative exists. You take a look at the ratio of the function difference over the variable difference, take the limit, and it's going to be equal to the derivative. That's what we learned in calculus. Ling does not use limits. So Ling uses a topological kind of definition. So you're going to have to do a little bit more. Ling's way of saying the limit is going to be the following. The way it's going to do is it's going to say that if I take a look at this function, and if my variable x is approaching a, but it's not exactly equal to a, then this limit is going to tend to f prime. So if you read this in the limit kind of format, it still kind of makes sense. For our talk, we don't need to go into the details of how this is defined. This is defined using the topological kind of knowledge and the terminology of filter, which I believe is probably from the Bourbaki textbooks. But this is what the Ling is sticking to. So for us, all we need to do is to understand that this is the limit. Okay, so we need to show that the derivative is less or equal to 0 at the left by using this new notation. So it's going to look a little bit weird. So the idea is that we're going to transform this limit going to a, but it's not equal to a. So both the limit on both sides, we're going to transform it to the limit from the left. And we're going to transform the limit from the left to the case when we are restricting to the interval from a minus theta to a. And apply the property of limits to figure out that the result is true at the end. So this part requires a little bit topology or the understanding of filter. But if you're just using the understanding of limits, try to understand all those tend to kind of statements using limits, then you are still going to be fine. After you've done this, then similarly, you can prove that derivative is greater or equal to 0. And at this stage, I'm just going to ask Ling to do the rest of the job for me because Ling already sees that something is less or equal to 0, something is greater or equal to 0. So you should know that this thing is equal to 0. So we're done with this. So the only tricky part over here is that you're going to have to work with a limit in a little bit trickier way that requires some more knowledge. I'm not going to show too much about the proof of Fermat's last theorem. There are several projects. I believe there has been researcher verifying Fermat's last theorem in a simple version. And then there is Bazard that's actually really trying to follow the whole idea of Andrew Wiles and finish the verification at the end. So you might be wondering why we would like to use Ling, as a prover. I mean, for me, the benefit is that it could correct my mistakes, obviously. When I do proofs, I like to do proofs, but I make mistakes. So if needed, putting it to Ling is going to help me with formalizing and verifying that proof is absolutely correct. But if you would like to ask me if I would recommend using Ling extensively, I'm going to say that it's up to you. For Ling, the thing is the following. It's easy to do something simple, okay, like the proof of Fermat's theorem I've just showed you. Just take a while to get used to this language, and try to work with something very simple. Then it's actually easy to pick it up and at least try to prove something straightforward. if you are interested in trying to do something really formal, or and in my words, you really hate making mistakes yourselves a lot, then you might take a look at it if you want to. The easiest way to start with is Lin's natural number game. So there is this is actually how I got addicted to it. It's addictive, by the way. I think the first couple of weeks when I was in touch with Lin, it's too addictive. I was not doing anything else. So what happens in this word, in this natural number game, is that you don't need to install anything. It's pure web based. You can do everything on the web, and the tutorial word is straightforward. It's gonna you basically just need to do whatever that you are told to do. Like the straightforward first step is try to show that this equation is correct, and it's almost immediate and trivial. You're done. And the goal of I believe your first word is to prove that 2 + 2 = 4, and then you can start moving forward from this word. You can try to learn some addition, try to learn some multiplication, power, some more addition, some inequality. And then at the end of the stage, I think it asks you to write the statement. In the web page, it says at the end we will see if we can prove Fermat's last theorem. This game was designed and was led by Kevin Bazar. So this makes perfect sense. By the end, it essentially only asks you to write down the statement of Fermat's last theorem, which is straightforward. So we can always start playing with Lin over here, just pure web based. And if you get really interested, then there is Lin. There is a Lin. What's the website? Lin Prover, I believe, is the post. I'm going to the chat room. This is the chat room of Lin. There is a website of Lin 4. Yeah, this is the website of the Lin community. It has actually a pretty good resource about telling you how to learn Lin. It started by introducing that natural number game, and if you would like to do something more, there are more tutorials that you can take a look. And whenever you get stuck, you can take a look at their Zulit channel. I tried to do everything all by myself in the first day or two. Turned out it was actually super difficult, even with the help of ChatGPT, and still not helping enough. But going to the forum, many questions could be answered really quickly. You might actually see my old posts with really naive questions that were done a couple months ago. So this is just a quick description of what this project is. Now, go from the single variable case to multivariable case. Obviously, you can think the extension to multivariable case should be straightforward. It is actually straightforward. What I wrote down previously, I mean, this a couple of lines of proof. Although it looks kind of straightforward, but you really don't need it. You can actually prove the statements I have just by one line, because Lin has a library called MATLAB. MATLAB has several theorems. So all you need to do is call a theorem, and your result is a special case of the theorem. So the exact theorem in MATLAB is actually saying that for multivariable case, Fermat's theorem is still true. There are more generalizations. For example, if the function is not differentiable, you can talk about some other. If the derivative does not exist, you can talk about some other more sophisticated cases, and still there are extensions of Fermat's theorem that still is true. Now, I don't think I have much time left. I'm just gonna say a little bit more about my research in optimization. I do optimization and I design algorithms. As you see, I mean, single variable case. I mean, in calculus, you can imagine, for example, the quadratic problem. You can try to compute the derivative equal to 0 really easily. Now, suppose that you are in multi-dimension and the dimension is like 1,000, 10,000, a million or more. There is no way for you to actually solve that gradient equal to 0. What are we going to do? Well, what we learned in calculus is that negative gradient direction is the direction along which function decreases the fastest locally. Okay, that's actually what we know. So always go negative gradient direction. You get your first algorithm. This is what I call nonlinear optimization algorithm 101. Given the current approximate solution, go negative gradient direction with a certain step size, get a new solution, keep doing until the end. So I've always used this to describe what I mean by algorithm design. So how do you compute the solution? You start with the initial guess of the solution, or if you're fighting a wild animal, start your first initial pose. And then all you need to do is compute, given any approximate solution, and throw a punch to your animal. So try to compute the gradient. And find a proper step size to go along that negative gradient, or try to control the body of the animal. In this case, a kangaroo. And get a new solution, or try to drag your kangaroo down or somehow. And try to check if the gradient becomes small later. And at the end, if it's not small enough, keep punching. So keep going. And if it's good enough, stop and output your solution, or go for your victory position, or whatever it is. Okay, so this is what I mean by iterative algorithm design. You do it step by step. This is the case when you cannot compute the gradient equal to 0. You're gonna have to do that numerically and iterative. Okay, and obviously for different kind of optimization problem, you're gonna have to do it in different way. I mean, you can't use one tactic for one wild animal. If it's a bear, you're gonna have to do something. I mean, if it's bear, you probably wanna take the back. If it's some other kind of animal, you probably want to do something else. For bear, you probably want to go the back, because the bear has short arms. That's a structure you can take care of to help you design your algorithm, and try to go for a choke and solve the solution. So this is what I mean by you're gonna have to take care of the problem structure in order to solve the problem. I don't really have time to play this game, but the idea is that even with all those kind of things, there is a big issue that if you do gradient descent, I can tell you that the gradient is always 0 in your gradient descent attempts. So think about doing gradient descent. You always go negative gradient direction. So at this, this is your initial guess. I'm going to tell you function value is 0, gradient is 0. You go to the next point. I'm going to say function value is 0, gradient is 0. You do it again. It doesn't really matter what you choose. I'm always going to tell you that the function value is 0 and the gradient is 0. Then you think you are at optimal solution. I'm going to start telling you that what you're seeing is actually wrong. I made it up for you. This is what the function look like. So all the function values and derivatives are going to be 0. So for general differentiable functions, it's actually pretty difficult to find optimal solution. In order to find optimal solution, you need the convexity. And that's something, although I plan to talk about, I don't have time. So let me actually just stop over here for now. And if you're interested, feel free to let me know. I'm still planning to see if we wanna. I mean, if we have enough interest, I would like to hold a small study group about using Lean to do some theorem proving of certain theorems that we're familiar with. Does not have to be in optimization. It could be number theory, analysis, whatever that you like to do. And I've been debating whether or not this should be a course, a special topic course but that depends on our interest. But anyways, that's everything that I have. Well, that's I'm out of time anyways. So that is summary. Thanks. Any questions?
Well, I have one, and this is just, I'm probably asking you just to conjecture. So I've heard speculation in both ends on this. How far away do you think the lean project is to when somebody submits a paper for publication, instead of sending it to a referee, they run it through lean?
That's a great question, and I hope I can have a partial answer for you. Let me pull out that paper. Let's see. Because I've actually done something similar. There is this very interesting problem in optimization. I think I talked about this theorem a couple years ago in MATLAB. It's basically, as soon as we teach you what is a convex set is a set that if you have 2 points in the set, draw the line segment. Line segment stays in the set. I do this all the time in 8100. I'm going to teach you that this is the definition. And then I'm going to tell you that there is this set. I want you to prove that it's convex. The proof is in this paper. So, that set has nothing that indicates that it's convex. But there are ways to prove that it is convex at the end. This is essentially it's 2-pager. I mean, if you follow this tree. If you follow the tree in other papers, it's probably a 2-pager or so as well. I chose a paper that I was interested, and I decided to do a proof myself. So this is my proof of Brickman's theorem. I actually copy and paste it to this talk that I had. This is something I planned for. So it starts from line 140, ends at 620. So it depends on you. I mean, if you think this is tolerable, it is tolerable. Not too much. Well, for me, it's actually a couple of weeks' work because I was not familiar with the link at the time. But this is essentially all you need to do to verify the proof of a 2-pager or 3-pager. I mean, if you think about Fermat's last theorem, that's going to be much more sophisticated. And this is actually something that I believe Terence Tao and Alex Kantanovich are trying to do at this stage. Because if you are doing number theory, the immediate non-trivial theorem that you can think of is the prime number theorem. So because prime number theorem, although it has an elementary proof, but elementary proof is really tricky. And if you really want to prove it using number theory, the terminology, you require some advanced techniques. So they are really trying to use Lin to verify the proof of prime number theory. That would be a good indicator about whether or not you can use that to verify papers in the future, I think. Right. Yeah. Right. Yeah. Yes.
So how much of the basic math that we're familiar with has already been verified?
Oh, that's
from the very ground up. Like you mentioned,
yeah,
prime number theorem. So I guess not that far yet.
Let me see. That's actually a great question. It depends on the participation, and I see more and more participants on this link project nowadays. On the link page, let me see. I think they have a statement over here about. I mean, we're just going to use undergraduate math topics over here. There is a list of undergraduate topics that are covered, and the topics that are not covered. It might be easier if you just take a look at the ones that are not covered. So there is a list of things that are covered and things that are not covered. For example, for my field in optimization, there was barely no research in that direction until a couple months ago. There are researchers in optimization that started building the formal verification of proofs like the convergence of gradient descent algorithm I just said. So the answer is that there has been progress, but at the same time, I think there are many things that are left to be done. A immediate thing I think I should mention is that I think Lin is really bad in things related to probability. So there are so lots of people are actually trying to move on that direction in the link community.
How low level are the like base definitions they're starting with? Like, are they actually constructing real numbers as Dedekind cuts and everything?
That's a great question. This is something I did not mention. Mathematicians, when we are trying to do link, we would like to start with the most general definition. And because if you prove the most general definition, you are done with the rest of it. Like the Fermat theorem that I'm showing. The proof was in the MATLAB was actually a Fermat theorem for, I think, over norm additive group or Hilbert space, I forgot. So the official ones that are included in MATLAB are really very general because they want to save the work amount so that you don't have to duplicate your work. But if you like to do things yourself, you can start from a really elementary level and just do whatever you wish.
Great. Other questions?
So it seems like you have different blocks and you're trying to like put all the blocks or some of the blocks together or something, and how that works. Then like suppose there are enough blocks, then how do you know which of them do you need? Or is a program like automatically?
So could you say the question again?
Like there are a lot of blocks like logically correct and you want to prove a new theorem.
Oh,
Then how can you just call them or say, okay, this is what I want to prove, and then you just find the blocks for me automatically?
that's true. Yeah, the thing is that when we are trying to prove something, all we need to do is use a list of previous knowledge, right? We don't actually, using link, you don't actually need to verify how it was proved, the previous knowledge. You don't need to know how it is proved. You only need to know that it has already been verified in link. The reason is because if it has been verified, then it is correct. And therefore, if you use that statement in your proof is also going to be guaranteed to be correct. So what I'm saying is that you can choose the block that you want from the available blocks. But you don't need to know how it is done. But you might be worried that if there are different statements of the same result, what should we do? Right?
Not really. It's just like I still need to be credited to build a proof, right?
That's true. That's true. So let me make it. I think I see your point. Link is a proof verifier or a interactive prover. It does not prove things for us. So
we're just building a huge library.
Essentially, we are building a huge library of existing results. Now, regarding the question about how we are going to be able to use link to prove something new, there has been attempts nowadays. The idea is using the large language models that are popular in machine learning. Essentially, what happens is that whatever whatever that's archived currently in the MATLAB library, you can essentially treat them as a certain mathematical language. And then using a large language model in machine learning, we're going to try to see if based on those current language, are we able to generate something new language. And the goal is basically using large language models so that for any new theorem that comes over, we're going to try to see if we can construct a valid proof. So this is ongoing work, and there are more and more publications in the community regarding automated proof using large language models and link nowadays.
So do they have lean for like people that don't believe in the axiom of choice? Lean to people that do, right? Do they have like blocks that say, if you believe in the axiom of choice, you can use this one. But if you don't, you need to, right?
That's going to be a really tough question. The reason is because it's going to be related to the foundation of link. Link's foundation is, I think it's a specific, it's dependent type theory, which is part of mathematical logic. And the philosophy, I think, in link is that whenever you state a theorem, you state a proof with the theorem, and then you build up the proof based on whatever ground you have. So they do have a whole library about the fundamentals of logic, but that's the part I'm not familiar with. I believe, if you'd like to, go toward the direction without using axiom of choice, there are possibility of building a library, but I'm not really sure if anyone has done that or not, because I did not search myself.
Or choice.
Okay, others? All right, well, let's thank our speaker again. Thank you. The grad student talking about some interesting stuff, so I'll let you all know on that. Y'all have a great weekend, and we'll see you on Monday. Well, right, maybe I'll see you.